This is the Satellite Foundational Course module on cyclogenesis and potential vorticity concepts. How can potential vorticity be inferred from satellite imagery? I'm Scott Lindstrom from SIMS. This 2025 update builds on the original course. Past contributors are listed. The learning objectives are listed on this slide. Take some time to read them. The satellite information you will see includes water vapor channels, the air mass RGB, and the split water vapor brightness temperature difference field. This figure shows the climatological distribution of potential vorticity. Latitude is on the x-axis, and the height in kilometers is on the y-axis. Potential vorticity has a reservoir in the stratosphere and variability with latitude. The dynamic tropopause is drawn in red. That's the height of the 1.5 potential vorticity unit surface. The dynamic tropopause generally exists lower in the atmosphere at higher latitudes, toward the poles, and at higher altitudes in the tropics. I'll also be showing the 2 potential vorticity unit surface, which is a little bit higher in the atmosphere. The transport of an upper tropospheric potential vorticity anomaly will affect low-level synoptic flow and produce vertical motions, usually by deformation on isentropic surfaces. The dynamic tropopause, that is the 1.5 PVU surface, extends to much lower altitudes in the vicinity of the upper-level potential vorticity anomaly. The anomaly there is that there are larger values of potential vorticity. Cyclogenetic events cause potential vorticity transport in the horizontal and in the vertical, and the higher ozone in the stratosphere can be traced. This classic figure from the 1985 Hoskins et al. Paper shows that the upper-level potential vorticity anomaly induces a low-level potential vorticity anomaly, and then the two anomalies grow in concert during cyclogenesis when strong upper-level forcing, as shown by the PV anomaly, is driving cyclogenesis. There is often a good correspondence between an upper tropospheric potential vorticity anomaly and dry or warm features as seen on the GOES water vapor imagery. This example shows pressures greater than 500 millibars along the 2 PVU surface in a region where mid-level dryness means the water vapor channel sees farther down into the atmosphere. So it's warmer. The warm feature to the west of Alaska is associated with a potential vorticity anomaly. If you look at the air mass RGB instead, potential vorticity anomalies typically have orange and red hues as shown here. This is a region of strong sinking motion that draws stratospheric ozone downward into the troposphere, as shown by this OMS imagery, and by NuCAPS retrievals. So both of them are showing more ozone in the troposphere because of the downward motion associated with the potential vorticity anomaly that shows up in the air mass RGB. Here's another example where we have the air mass RGB that's in a region where we have a ozone anomaly as diagnosed by NuCAPS, and the pressure on the 2 PVU surface there is larger, so you're farther down in the atmosphere. GOES imagery for the same time, bands 8, 9, and 10, and the air mass RGB show the characteristic signal of a PV anomaly that is accompanied by mid-level drying. Or you might want to use this enhancement. Features in the water vapor imagery associated with PV anomalies can cause cyclogenesis. In this example, the phasing of an impulse dropping down in the northern stream with an impulse in the southern stream causes strong cyclogenesis off the west coast of North America. So you're looking at the water vapor imagery here, but what you're seeing is a potential vorticity anomaly dropping southward out of Alaska. There are many examples that show air mass RGB imagery with red and orange features that are showcasing a feature in the split water vapor imagery, which is the red component of the air mass RGB. Here we see a pressure analysis on the 1.5 PVU surface. The largest pressure contour on the 1.5 PVU surface is 575 millibars. This is showing extratropical transition as that potential vorticity anomaly interacts with the tropical cyclone. 12 hours later, the extratropical transition of the storm continues. Now there's a 600 millibar contour in the pressure analysis on the 1.5 PVU surface. And 12 hours later, it's down to 625 millibars. Descent in the atmosphere accompanies the strong extratropical cyclogenesis. For more information on Leslie, that's the storm here that's transitioning, see the link to the SIMS blog post. PV anomalies frequently accompany extratropical transition of tropical cyclones. Look in the mid-latitudes for red and orange signals in the air mass RGBs that are approaching the tropical cyclone environment. Links to animations of some events are listed here. There's also a comment learning module on Merbach and its impact on Alaska after transitioning to a powerful extratropical storm. Here's a summary of key points discussed in this training. GOES-R satellite imagery, specifically air mass imagery, the split water vapor difference, and the individual water vapor channels can all help diagnose where potential vorticity intrusions in the troposphere are occurring. These are regions where strong cyclogenesis might occur. You can find additional information pertaining to water vapor imagery, the air mass RGB and split water vapor difference products, and PV anomaly cases at the links listed here. The links are also available in the launching page of this module. This concludes this training. Thanks for listening.